Imagine you are holding a freshly sliced, perfectly ripe tropical pineapple. Bring it right up to your nose. You know that smell, right?
Oh, absolutely. It's unmistakable.
Yeah, it's sweet, it's vibrant, it instantly makes your mouth water. Your brain receives that chemical signal and immediately categorizes it as, delicious, safe, and nutritious.
Right. Your body is essentially telling you, yes, consume this.
Exactly. But now I want you to imagine opening a container of butter that has been sitting out in the hot sun for like 3 weeks. It is utterly rancid. The smell hits you and you physically recoil.
You gag. I mean, it's a completely automatic reaction.
Yeah, your biological alarm bells are just screaming at you that this is poison, this is decay, do not put this in your body.
It really is one of the most visceral reactions we have as humans.
Yeah.
Our olfactory system, our sense of smell is incredibly aggressive when it comes to self-preservation.
Right. But here's the thing that completely broke my brain when we started looking into the research for today's deep dive. The chemical responsible for that gag-inducing, rotting butter smell and the chemical responsible for that sweet tropical pineapple smell are virtually identical.
It's wild to think about, really.
It is. On a microscopic level, they are separated by just one tiny, almost insignificant structural tweak. You change one tiny attachment on the molecule, and your brain flips from biohazard to fruit salad.
It's a complete neurological 180.
So, welcome to the deep dive. Today, we are going to explore a category of molecules that you, the listener, interact with every single day. Something you literally cannot survive without, yet something we constantly misunderstand. Lipids.
Yeah, it is a phenomenal area of biochemistry to look at because lipids are, well, they're the ultimate multitaskers of the natural world.
Okay, let's unpack this. We have a massive stack of biochemical research, structural formulas, industrial food science. What's our mission here?
Well, what's fascinating here is that when you actually get down to the molecular level, you realize that nature is incredibly efficient. It doesn't invent, a million different tools for a million different jobs.
Right, it doesn't have the energy for that.
Exactly. It creates one highly adaptable structural foundation and just makes slight modifications to build entirely different aspects of life.
Which is exactly what we are going to do today. We are going to demystify fats and oils. We're going to figure out what they look like on a microscopic level, where they come from, and how they build our bodies.
And we'll also get into how humans have learned to chemically alter them, which is a whole other fascinating story.
Oh, yeah. Throwing heavy metals and hydrogen gas at them to engineer our food supply. But we really have to start at the foundation, right? Because before we can understand what fats and oils do, we have to understand what they actually are.
Right. And to understand how a single class of molecules can do so many different things, you have to understand the architecture. In biochemistry, lipids are classified as macromolecules.
See, macromolecule always sounds to me like a buzzword. It just means a big molecule, right? But how big is big when we're talking about the microscopic world?
That's a great question. We're talking about hundreds of atoms assembled into a very specific shape.
Okay, so hundreds.
Yeah, they are massive compared to something like, say, a water molecule, which is just 3 atoms, right? 2 hydrogens and an oxygen.
Right, H2O. Very simple.
Exactly. But despite their size, the core structure of a lipid, specifically the oils and fats we consume, is remarkably elegant. Fundamentally, these oils and fats are esters of long-chain carboxylic acids bound to glycerol.
Okay, stop right there. I know I promised we were going to make this approachable, and you just dropped esters of long-chain carboxylic acids on us. Let's translate that.
Fair enough. That sounds intimidating.
Let's start with the carboxylic acid part. What actually is that?
Okay, let's break it down. A carboxylic acid is essentially a long string of carbon atoms. Think of it like a train, where every car is a carbon atom linked to the next one.
Okay, I can picture a long train.
And all along this train, you have hydrogen atoms clinging to the sides. But what makes it an acid is the very last car on the train.
The caboose.
Right, the caboose. That final carbon atom is double bonded to an oxygen atom and single bonded to a hydroxyl group.
Wait, what's a hydroxyl group again?
Oh, that's just an oxygen and a hydrogen together. So that specific caboose on the molecular train is called a carboxyl group.
So because of that specific caboose, it behaves like an acid. Like it can donate a hydrogen ion.
Precisely. In the context of lipids, we call these long-chain carboxylic acids fatty acids. They're the primary building blocks.
Oh, okay. Fatty acids. I've definitely heard that term on nutrition labels.
We all have, yeah.
Yeah.
But here is the crucial thing. In your butter or your cooking oil, These fatty acid chains aren't just floating around freely by themselves.
Why not?
Well, if they were, your butter would actually be highly acidic and corrosive, which, obviously it isn't.
Right, it doesn't burn my tongue when I eat toast, so they must be anchored to something else.
Exactly. They're anchored to glycerol.
Okay, glycerol. When I was looking at the structural diagrams of this in the source material, the shape really jumped out at me. I want you, the listener, to picture a wooden coat rack standing in your hallway.
It's a good visual.
It's just a simple vertical post. Now, this specific coat rack has exactly 3 hooks on it, one stacked above the other. That vertical coat rack is the glycerol molecule.
I think that's a very helpful way to visualize the spatial arrangement. Glycerol itself is a relatively small molecule. It's a type of sugar alcohol, structurally just a 3-carbon chain where each carbon has a place to attach something else.
Your 3 hooks?
Your 3 hooks, yes.
Exactly. And hanging off each of those 3 hooks is a massive, heavy, floor-length winter coat.
I love this analogy.
Thanks. Those coats are the fatty acids we just talked about. Those long trains of carbon and hydrogen.
And the mechanism of how the coats hang on the rack is where the actual chemistry happens. You mentioned earlier that the definition of a fat or oil is an ester.
Right, you said they're esters of long-chain whatever.
Esters of long-chain carboxylic acids, yeah. An ester is just the chemical name for the bond that forms when an acid, which is our fatty acid coat, attaches to an alcohol, which is our glycerol coat rack.
Okay, so how does that attachment actually happen? Do they just bump into each other in a cell and, stick together?
Not quite. It requires a specific chemical reaction called dehydration synthesis.
Dehydration, so it loses water.
Exactly. When the carboxyl group on the fatty acid comes up to the hook on the glycerol, they kind of negotiate. The glycerol gives up a hydrogen atom, and the fatty acid gives up an oxygen and a hydrogen.
Oh, I see. 2 hydrogens and 1 oxygen.
Yep. Together, those discarded atoms form H2O, water. The water floats away, and the fatty acid is now firmly chemically bonded to the glycerol.
That is so cool. And because there are 3 hooks on the glycerol, this happens 3 times.
Which is why the resulting macromolecule is called a triglyceride.
Ah, triglyceride. Tri for the 3 fatty acid coats, and glyceride for the glycerol coat rack. 3 coats securely hooked onto 1 rack.
You got it. And this reaction doesn't just happen instantly on its own. In nature, it's governed by enzymes. But if you were doing this in a laboratory setting, the research notes that you need to use a mineral acid as a catalyst to make it happen efficiently.
A mineral acid, what, like hydrochloric acid or sulfuric acid?
Yes, exactly. A catalyst is essentially a chemical matchmaker. It lowers the energy barrier required for the reaction to take place without actually getting consumed in the process itself.
So it just helps the reaction along.
Right. So you put your glycerol, your fatty acids, and a bit of mineral acid together, provide the right conditions, and you assemble your triglycerides.
And this single structure, this heavily loaded coat rack, is the physical foundation for almost every single fat and oil on the planet. I mean, it is wildly efficient. Nature just figured out how to bundle these long, unwieldy carbon chains into manageable groups of 3.
It really creates an incredibly dense, stable package. By neutralizing the acidic ends of the fatty acids through that ester bond, the resulting triglyceride is largely non-reactive. It's incredibly stable.
Perfect for storage.
Yes, it is the perfect long-term storage container for biological energy.
Which brings us to the great divide. We have the microscopic architecture down, but when I walk into my kitchen, I don't see microscopic coat racks.
No, you definitely don't.
I see a solid block of butter in the fridge, and I see a puddle of olive oil on the counter. We inherently categorize these things by their physical state, right? Solid equals fat. Liquid equals oil.
That's the standard everyday definition, yes.
But for a long time, I never understood why one is solid and one is liquid. They are both just triglycerides, right?
They are, both of them. The difference lies entirely in the tailoring of those fatty acid coats. The research draws a very definitive line in the sand here.
Let's hear it.
Fats, which are the solids at room temperature, are triglycerides made up of saturated fatty acids. Oils, the liquids at room temperature, are triglycerides made of unsaturated fatty acids.
Okay, I have to push back here, because this is where a lot of textbook definitions just stop, and it's maddening.
I know exactly what you mean.
People hear, saturated fats are solid and unsaturated fats are liquid, and they just accept it as a rule. But why? How does a microscopic detail about saturation magically dictate whether a substance melts on my kitchen counter? What is the actual mechanism?
To really understand the mechanism, we have to look closely at the carbon chains themselves. Remember that chain of carbon atoms we discussed?
The train.
The train, right? Carbon atoms love to bond with things. They each have 4 available connection points. In a saturated fatty acid, every single carbon atom in the chain is holding hands with its neighboring carbons in front and behind it.
Okay, so that uses up 2 connection points.
Exactly. And it uses its remaining 2 hands to hold on to hydrogen atoms. It is completely saturated with hydrogen. It literally cannot hold anymore.
Okay, so it has a maximum payload of hydrogen, but what does that mean for its shape?
It means the chain is incredibly straight. It forms a neat, orderly zigzag line. Now think about those straight chains attached to our glycerol coat rack.
Okay, I'm picturing it.
If you have a bunch of saturated triglycerides floating around next to each other because their tails are perfectly straight, they can pack together extremely tightly.
Ah, like Pringles in a can.
That is a brilliant way to think about it, yes.
Yeah.
They stack perfectly flush against one another.
So they just lock in.
Right. And in chemistry, when molecules pack together tightly, the intermolecular forces between them, specifically something called London dispersion forces, become very strong.
London dispersion forces. Sounds fancy.
It does, but it basically just means they lock each other into place. Because they are locked together tightly, it takes a significant amount of ambient heat energy to shake them apart. Therefore, at regular room temperature, they remain a solid.
So a saturated fat is solid because its molecular chains are physically straight and they stack like bricks. That makes perfect sense. So what is happening with an oil? What makes a fatty acid unsaturated?
In an unsaturated fatty acid, somewhere along that carbon chain, 2 adjacent carbon atoms decide to form a double bond with each other.
Wait, they use 2 hands just to hold on to each other?
Exactly. And because they are now using 2 of their connection points just to hold on to each other, they don't have enough hands left to hold as many hydrogens. It is not fully saturated with hydrogen.
And how does that double bond change the physical shape of the chain?
It creates a severe kink, a bend in the chain. It's no longer a straight, orderly line. Imagine your can of Pringles. But every third chip is violently bent at a 45-degree angle.
Oh, wow. You wouldn't be able to stack them. They wouldn't fit in the can. There would be tons of empty space between them.
Exactly. Because the unsaturated triglycerides have these bent, kinked tails, they cannot pack tightly together. They constantly push each other away, leaving microscopic gaps.
That makes total sense.
Yeah, and because they can't lock together tightly, those intermolecular forces are much weaker. It takes very little heat energy to keep them moving around. So at room temperature, they just flow past each other. They exist as a liquid oil.
That is incredible. So the melting point of my butter versus my olive oil is entirely dictated by molecular geometry. The straight tails stick together, the bent tails slide around.
It's all about shape.
Yeah.
And just to give you a sense of the scale of these molecules, the research highlights 2 specific examples of saturated fatty acids, palmitic acid and stearic acid.
Okay, palmitic and stearic.
Palmitic acid has the formula C15H31COH. Stearic acid is C17H35COOH.
Whoa, C15 and C17. That means there are a solid 15 or 17 carbon atoms lined up in a row, just dragging behind that carboxyl group.
Right, and because they are saturated, they are perfectly straight chains of 15 or 17 carbons. When you build a triglyceride out of stearic acid, you have that tiny glycerol backbone managing 3 massive 17-carbon-long street tails.
That sounds huge.
It's a dense, heavy molecule, which is why substances rich in stearic acid, like beef tallow or cocoa butter, are very hard, rigid solids at room temperature.
Which leads to a really interesting question. We know these molecules are massive, right? Assembling a 17-carbon chain takes a significant amount of biochemical effort. Nature doesn't expend energy for no reason.
Definitely not.
So why do biological systems bother building these giant heavy coat racks in the first place?
Well, the return on biological investment is staggering. The primary biological superpower of lipids, as we all generally know, is energy storage. Fats and oils are incredibly high-energy foods.
Let's unpack why they are high energy. Because gram for gram, fat has more than double the calories of carbohydrates or proteins, right? Why is the energy density so much higher in a lipid?
It comes down to oxidation. The energy our bodies extract from food comes from breaking chemical bonds, specifically the bonds between carbon and hydrogen, and reacting them with oxygen.
Okay.
Carbohydrates, by definition, already contain a lot of oxygen. They are partially oxidized before you even eat them. But lipids, those long 15 and 17 carbon tails, are almost entirely just carbon and hydrogen. There's virtually no oxygen in the tail.
So they have significantly more carbon-hydrogen bonds available to be broken and oxidized in our cellular engines.
Exactly. They are a much purer fuel source.
That makes a lot of sense.
But Their biological utility goes far beyond just being a calorie battery. If we connect this to the bigger picture, the research explicitly highlights that lipids are the essential delivery mechanism for crucial vitamins, specifically vitamins A, D, and E.
Right, because those are fat-soluble vitamins. But what does that practically mean for human biology? Like, if I eat a carrot packed with vitamin A, but I don't eat any fat with it, what happens?
Honestly, your body struggles to absorb it. The text notes that lipids are insoluble in water, but soluble in organic solvents, meaning other fats.
Okay, and our digestive tract is mostly water.
Very watery environment.
Mm-hmm.
And vitamins A, D, and E are hydrophobic, meaning they don't dissolve in water. So if there are no lipid molecules present in your digestive system to bind to those vitamins, dissolve them, and escort them across the intestinal wall into your bloodstream.
Wait, they just leave?
Yeah, those vitamins largely just pass right through you unabsorbed. You absolutely need the lipid to act as a transport vehicle.
So they are fuel and they are logistics vehicles.
Yeah.
But the structural aspect is where my mind was completely blown. We think of fat as just sitting there, right, storing energy. But the research points out that lipids are used to physically build brain cells, nerve cells, and the membranes of every single cell in your body.
They are the literal structural bricks of biology. To build a cell membrane, the body modifies our triglyceride coat rack just slightly.
Oh, so?
It takes off one of the fatty acid coats and replaces it with a phosphate group, creating what we call a phospholipid. Because the phosphate end loves water and the two fatty acid tails hate water, they spontaneously arrange themselves into a double layer, a spherical wall.
So they naturally form a bubble.
Exactly. Without lipids, you literally cannot build a biological cell.
And beyond just the walls of the cells, I was staring at this part of the research regarding nerve cells. It casually mentions that fat stored in the body insulate it because they are poor conductors of heat and electricity.
Yes.
And I sat with that for a minute and a light bulb went off. Think about the wiring in your house. You have a copper wire carrying the electrical current, and wrapped entirely around that copper wire is a thick rubber casing.
The insulation.
Right, and the rubber is there to keep the electricity flowing straight down the line so it doesn't short circuit into the drywall or zap you if you touch it. Are lipids essentially acting as the biological rubber casing for our nervous system?
That is a phenomenal analogy, and it is chemically entirely accurate. Your nervous system operates on electrical impulses called action potentials. When your brain tells your finger to move, an electrical charge shoots down the axon of your nerve cell.
Okay.
If that nerve cell were bare, the electrical charge would leak out into the surrounding watery tissue, and the signal would degrade or disappear before it ever reached your finger.
So the body wraps the nerve cell in fat.
Specifically, it wraps it in something called a myelin sheath, which is constructed almost entirely of lipids. Remember, lipids are completely insoluble in water, and they have no free electrons to carry a charge.
So they can't conduct electricity.
Right. They are the perfect biological insulator. They wrap around the nerve fiber like that rubber casing you mentioned, preventing the electrical signal from leaking out, which actually allows the impulse to travel exponentially faster down the line.
It is stunning to me that the exact same foundational molecule, that glycerol coat rack, is simultaneously acting as a high-density fuel source, the transport truck for your vitamins, the structural brick for your cellular walls, and the rubber electrical insulation for your brain.
It really is the ultimate testament to the versatility of organic chemistry. By simply adjusting the length and the saturation of the coats on the rack, biology has solved dozens of distinct problems.
Which naturally leads us to look at where all this manufacturing is happening. Knowing how essential these molecules are for life, diverse ecosystems all over the planet have evolved different ways to synthesize and store them. Let's look at the factories of the natural world.
Right, the sources.
The research categorizes them into animal, plant, and marine sources. Let's start with the land animals.
Well, in the animal kingdom, mammals primarily synthesize saturated fats.
Right.
And this is because they maintain a warm body temperature that keeps those fats somewhat fluid internally, and they store them in specialized adipose tissue cells.
Which is the body fat we are all familiar with. But humans realized a long time ago that we don't just have to harvest the adipose tissue. Mammals also secrete milk. And the research specifically highlights that from milk, we obtain butter and ghee, which have become, cornerstones of human culinary history.
Absolutely. They are used for cooking, frying, baking sweets. But there is a fascinating pivot in the data here. It notes that alongside culinary uses, animal fats are a primary raw material for the soap industry.
I was wondering if we were going to touch on this. It seems so counterintuitive, right? That you would use greasy, slippery animal fat to make something that cleans you. How does that work?
It involves a process called saponification. We talked earlier about how the triglyceride is formed by an ester bond, hooking the coats onto the rack.
Yeah, the dehydration thing.
Saponification is violently ripping those coats back off. Industrially, you take animal fat and you boil it with a highly caustic strong base, like sodium hydroxide. Lye.
So you are basically attacking the ester bond.
Exactly. The lye shatters the ester bond, it separates the glycerol backbone, and the sodium from the lye attaches to the free fatty acid chains, creating a salt.
A salt. Wait, soap is a salt.
Chemically, yes.
Yeah.
That fatty acid salt is what we call soap. It's brilliant because one end of the soap molecule, the salt end, loves water, but the long carbon tail still loves oils and grease.
Oh, so it bridges the gap.
Right. So when you wash your hands, the tails stab into the dirt and grease on your skin, the water-loving heads pull it all up into the running water, and it washes away.
So you literally dismantle the triglyceride to weaponize the fatty acid chains against dirt. That is amazing. Now let's look at the plant kingdom. Plants are also pumping out lipids, but the research points out they store them entirely differently.
Yes, they do.
They synthesize oils and store them primarily in their seeds. Examples like sunflower oil, coconut oil, groundnut, and corn oil.
And we really have to ask why plants put their oils in seeds while animals store fat and tissue.
Yeah, why is that?
It goes back to energy density. A plant seed is a baby plant that is completely cut off from an energy source. It doesn't have leaves yet, so it can't perform photosynthesis. It needs to pack the maximum amount of biological fuel into the smallest possible space, so the seedling has enough energy to grow out of the dirt and reach the sun.
And as we established, lipids are the most energy-dense fuel available. So the sieve is basically a biological battery packed with oil. But why oil? Why are plant lipids mostly unsaturated liquids, while cow fat is a solid?
It all comes down to ambient temperature. A cow has an internal body temperature of around 101 degrees Fahrenheit. At that temperature, saturated fats are pliable enough to be metabolized.
Okay.
But a sunflower seed might be sitting in the ground in early spring when the soil is, say, 45 degrees. If a plant used saturated fat, it would freeze into a solid, impenetrable brick inside the seed. The plant's cellular machinery wouldn't be able to access it.
Ah. So the plant intentionally introduces double bonds, those kinks we talked about, to create an unsaturated oil that will remain fluid and usable even in cold soil.
Exactly. The molecular geometry is an evolutionary adaptation to ambient temperature.
Which provides the perfect transition to the third category of factories. Marine organisms. The research specifically isolates salmon and whales as massive sources of oils. And earlier, I was confused by this, because a whale is a mammal, like a cow.
True.
But a cow produces solid saturated fat, and a whale produces massive quantities of liquid unsaturated oil. But based on what you just said about the plant seeds, I think I understand why.
We'll put the pieces together. What is the whale's environment?
The whale is swimming in the Arctic Ocean. The water is freezing. If a whale insulated itself with the same saturated fat that a cow uses, the moment it dove into freezing water, its blubber would crystallize and turn into solid rock. It wouldn't be able to move.
Spot on. Marine mammals must maintain fluidity in their lipid stores at extreme cold temperatures. Therefore, marine biology utilizes highly complex, highly unsaturated fatty acid chains, things like omega-3s.
So they need the kinks.
The extreme cold demands a severely kinked molecular structure, so the molecules can't pack together and freeze.
And the structural difference translates directly to human use. The research notes that while animal fats are for baking and plant oils are for cooking, marine oils, specifically cod liver oil, are traditionally utilized for medicine.
Because humans historically recognized that the specific nutritional profile of these highly unsaturated marine oils provided biological benefits. Things like joint inflammation reduction and high vitamin D concentration. You just couldn't get that from a saturated block of lard.
The environment dictates the chemistry, and
Right.
the chemistry dictates the application. It's beautiful. But of course, humans are never satisfied with the boundaries set by nature.
We rarely are.
We look at a bottle of liquid sunflower oil and think, what if I want to spread this on toast like butter? We want to change the physical state. And the research details exactly how we do this through a process called hydrogenation.
This is one of the most significant industrial food engineering developments of the 20th century, taking a liquid plant oil and chemically forcing it to behave like a solid animal fat.
Here's where it gets really interesting, because I want to break down how violent and intense this process is. We take margarine and shortening for granted. But the research says we are taking vegetable oil, which is an unsaturated tree ster, and turning it into vegetable ghee, a saturated tester.
Yes.
We know that to go from unsaturated to saturated, we have to eliminate those double bonds in the carbon chain. We have to straighten out the kink Pringles.
Correct. And to do that, you have to break the double bond and plug the empty spots with hydrogen atoms.
Right. But the text says you react the oil with hydrogen gas, H2, in the presence of a nickel catalyst at 250 to 300 degrees Celsius. That is nearly 600 degrees Fahrenheit. Why do we need heavy metal and massive heat to make this happen? Can't we just bubble hydrogen gas through cold oil?
Hydrogen gas on its own is very stable. It exists as H2, which means two hydrogen atoms tightly bonded to each other. If you just bubble it through oil, it will float right to the top and escape. It doesn't want to react with the carbon double bonds.
Oh, I see.
This is where the nickel catalyst comes in.
Okay, what is the nickel actually doing on a molecular level?
Think of the nickel as a molecular anvil. When you introduce the hydrogen gas to the solid nickel surface under immense pressure, the nickel temporarily grabs onto the hydrogen molecules and actually forces the HH bond to break apart.
Whoa!
So now you have individual, highly reactive atomic hydrogens stuck to the surface of the metal anvil.
So the nickel has basically prepped the hydrogen, made it aggressive and ready to attach.
Yes. And then, under that extreme heat of 250 to 300 degrees Celsius, which is required to get the massive lipid molecules moving fast enough, the unsaturated fatty acid chains smash into the nickel surface.
And then what?
The double bonds in the carbon chain hit the reactive hydrogen atoms, the double bond breaks open, and the carbons grab the hydrogens.
And boom! The kink is gone. The chain straightens out.
Exactly. The molecule falls off the nickel surface, but now it is saturated. It is straight. You do this millions of times over, and suddenly the molecules compact tightly together. You turn the heat off, let it cool to room temperature, and what was a puddle of liquid oil is now a solid block of vegetable ghee.
It is stunning industrial alchemy. We use heavy metal and superheated gas to physically hammer straight the molecular structures of plant food, and the research makes a fascinating distinction regarding temperature and product control. We just talked about vegetable ghee needing 250 to 300 degrees, but then it talks about margarine.
Right. Margarine utilizes the same chemical principles, hydrogenation with a catalyst, but the text specifies it is processed at 200 degrees Celsius.
A 50 to 100 degree difference in the manufacturing reactor changes the entire classification of the product. And the research provides a golden rule for this. Greater the amount of hydrogen added, the more solid the margarine becomes.
Which perfectly aligns with our Pringles analogy from earlier.
Right.
If you only partially hydrogenate the oil, like maybe you straighten out half the kinks but leave the other half alone, you get a substance that is semi-solid, it's softer. It spreads easily right out of the fridge.
But if you go all the way...
If you fully hydrogenate it, hammering out every single kink, it becomes a rigid, hard block of shortening.
So we are literally dialing in the exact physical texture and spreadability of our food by adjusting the volume of hydrogen gas and the temperature in a chemical reactor. It completely strips away the illusion of simple foods. That tub of margarine isn't just food, it is a highly engineered chemical product designed to mimic the exact molecular geometry of a cow's saturated fat, using a sunflower as the raw material.
It really is chemistry applied to sensory experience and convenience.
Which brings us perfectly to the final and frankly most mind-bending part of our deep dive today. We have talked extensively about how molecular structure dictates whether something is a solid or a liquid, how it stores energy, how it insulates nerves. But the research concludes with an example of how a tiny chemical tweak dictates something entirely subjective, our sense of smell.
This is where biochemistry intersects with human neurology in a way that feels almost like magic.
We brought this up in the intro. The research presents a molecule called butanoic acid. It explicitly notes that butanoic acid is the chemical responsible for the foul smell of rancid butter.
And we should clarify, butanoic acid is exactly what it sounds like. It is a short-chain carboxylic acid, just 4 carbons long.
Okay, so it's a very short chain.
Yes. When butter spoils, bacteria break down the triglycerides and cleave off these short fatty acids. When they become free-floating, they become volatile, meaning they evaporate into the air easily and enter your nasal passages.
And when they hit our nose, the biological response is intense. Vomit, rotting dairy, severe decay. It is one of the most universally repulsive smells to human beings.
Because evolutionarily, our olfactory system is a hazard detection system. Our brain has evolved a specific receptor for butanoic acid, and when that receptor is triggered, the neurological translation is, this food is degraded, it's full of bacteria. If you eat this, you'll become violently ill. It induces a gag reflex to prevent ingestion.
But then the research offers this insane twist. It says that if you take this vile butanoic acid and you react it with an alcohol to form an ester, the smell completely transforms. It becomes fruity.
Specifically, it forms an ester linkage. You're replacing the hydrogen on the carboxyl end of the acid with a short carbon chain from an alcohol.
The text gives two exact examples. It says if you form methylbutanoate, which just means adding a tiny one-carbon methyl group, it smells exactly like an apple.
Yes.
If you form ethylbutanoate, adding a two-carbon chain, it smells exactly like a fresh pineapple.
Let's truly contextualize this. You are taking the molecule of vomit, of rancidity. You are snapping off a single hydrogen atom and clicking on a single carbon atom in its place. And the result is the smell of a ripe apple.
How is that neurologically possible? How can a one-atom difference completely invert the signal from biohazard poison to delicious, nutritious fruit?
It has to do with the lock and key mechanism of our olfactory receptors.
Lock and key.
Yeah, the receptors inside your nose are physical structures. They are microscopic locks. The scent molecules are the keys. A receptor only fires an electrical signal to your brain if a molecule with the exact right 3D physical shape fits into the lock.
Okay, so shape is everything.
Butanoic acid has a very specific shape. It fits perfectly into the rotting food receptor lock. But when you add that methyl group to create methylbutanoate, you have physically changed the 3D geometry of the molecule, even slightly. It is no longer the same shape key.
Ah, so it literally no longer fits in the rotting food lock.
Exactly, it bounces right off it. But the new shape happens to be the exact perfect fit for a completely different receptor lock right next door, the right fruit receptor.
That is wild.
The molecule clicks into that new lock, fires a completely different electrical pathway to a different part of your brain, and your consciousness perceives apple.
It is absolute biochemical wizardry. Just altering the functional group of a molecule, adding a methyl or ethyl group, flips the biological script. Nature is taking the same base molecule, slapping a tiny piece of carbon on the end, and creating an entirely new sensory experience.
It perfectly illustrates how precise and unforgiving the language of chemistry is. A single structural alteration fundamentally changes the molecule's identity and how it interacts with the entire biological world.
So let's pull all the threads together. So what does this all mean? We started this deep dive talking about how simple our kitchen pantries seem. You have solid butter for baking, you have liquid oil for frying. We think of them as totally separate things.
But the reality is a unified, highly adaptable system.
Right. We zoomed all the way down to a microscopic glycerol backbone, that three-hook coat rack. We saw that if you hang perfectly straight, saturated fatty acid chains on it, they pack together tightly like Pringles in a can, locking into a solid block of fat. If you introduce a double bond, creating a kink, they can't pack together and they flow freely as a liquid oil.
We saw how those exact same triglyceride structures are dense enough to provide massive amounts of biological energy.
And versatile enough to transport vital fat-soluble vitamins like A, D, and E.
And waterproof enough to act as the literal rubber insulation wrapping around our neural wiring to keep our brains from short-circuiting.
We tracked how nature utilizes this chemistry based on environment. How a cow's warm body allows for saturated fats, how a plant seed in cold dirt requires liquid oil to sprout, and how a whale in the freezing Arctic Ocean relies on highly complex unsaturated blubber just to survive.
And we also witnessed human industrial alchemy, blasting plant oils with hydrogen gas and a nickel anvil at nearly 600 degrees Fahrenheit to physically hammer out the kinks and engineer our own solid fats like margarine.
And finally, we saw how the exact same structural logic applies to human perception, where just turning a short-chain carboxylic acid into an ester flips the switch in our brain from the stench of rancid butter to the sweet aroma of a tropical pineapple.
It truly is a testament to the elegant efficiency of the natural world. Everything we interact with, taste, smell, and use to fuel our bodies is governed by microscopic geometry.
And it leaves me with one final thought, something for you, the listener, to ponder the next time you're standing in your kitchen staring at your pantry. If the exact same fundamental building blocks can make up the cell membranes that allow you to form a thought, the thick blubber that keeps a whale warm in the darkest depths of the ocean, and the ester that mimics the smell of a fresh pineapple, it begs the question.
What's that?
What other everyday materials in our lives, things we take completely for granted, are just one tiny microscopic chemical tweak away from being something entirely shockingly different?
When you realize that reality is built on such precarious and precise molecular foundations, the entire world around you suddenly feels a lot more magical.
It really does. Thank you for joining us on this deep dive into the hidden architecture of lipids. Remember to always question the simple categories and stay curious.